Hi, welcome to another Algebra 1 video. In this video we're looking at section 3.6, part 2, which is linear function transformations. In this video we will learn about the reflection transformation in linear graphs. We will learn about the lines of reflection, and we will also learn about reflections in linear equations. So let's talk about the reflection transformation in linear functions. In part 1 of linear function transformations, we learned about the translation transformation, in which we learned that the parent function of all linear equations is represented with y equals to x. We also learned that every other function that you get outside of y equals to x, the parent function is a derived function. And some examples of such functions could be y equals to 2x. You could come up with y equals to x plus 1. Or you could come up with y equals to negative x plus 5. In the previous video, we specifically talked about the translation transformation, specifically in horizontal and vertical translations. We know that horizontal translations can be represented by the general equation of y equals to x minus h plus some value if you want to include that. And for vertical translations, we know that our function y would equal to the x value, which is not changed, but you're changing the value of the entire function y by adding some constant k. And we also learned that you can combine these two types of translations, the horizontal and vertical translations, to make a combined translation of the parent function. So you could come up with a function with the form y equals to x minus h plus k. In this case, we have combined the negative h, where your value of h, depending on its sign, tells you if you're shifting the function to the right or to the left. And your k value, if it's positive, means you're shifting it upwards, and if it's negative, you're shifting it downwards. And so we can come up with another function, which would be a combined translation of the parent function y equals to x. And we could say that it's y equals to x minus 5, where 5 is our h. And then we can add some constant k, say 6. So we're shifting that function upwards by 6. But what about the transformation of reflections of linear functions? Graphically, the reflection transformation in linear functions is a transformation that flips a line along a line of reflection. And most commonly in linear function transformations, you're only going to be reflecting along the x-axis, which is this axis, or you could be reflecting your line that is graphed along the y-axis. So let's look graphically what a reflection of a line is. Let's say that you had graphed the line f of x equals to x, which is also known as y equals to x. In this case, let's say that you wanted to reflect this line across the x-axis. Before we do that, let's mark some points on the parent function f of x equals to x. For the parent function, we know that all of your x values, whatever you plug in for x, will equal your y value, or f of x. So if you plug in 2 for x, your f of 2 will also be 2. And you could also graph f of negative 2, which would also give you negative 2 for your y value. So the points 2, 2 and negative 2, negative 2 would lie here and here. And we know that we're reflecting this line y equals to x along the x-axis. So our axis or line of reflection will be the x-axis in this case. So here I have marked my axis of reflection. If you pretend that you're standing at the point of negative 2, negative 2 on this coordinate plane, and you look into this mirror, which is the x-axis, then we know that your reflected point will appear to be at this point here, above the axis. So in this case, your point negative 2, negative 2 that you had on the original function f of x equals to x will move to this point over here, which is now negative 2, positive 2. So we can see that your x value has remained the same, as negative 2 was also here, but your y value has flipped from negative 2 to the positive 2. And if we look at the second point over here, 2, 2, we know that if you pretend that you're standing here and you're looking at the mirror down here, then your reflection will appear to be behind this mirror over here. And that reflected point will be given by the point 2, negative 2. So before we reflected this point, here we had 2, 2 where both values were positive, and in the reflected point our x values are still the same, but our y value in this case has switched from positive 2 to negative 2. And if you connect the dots using the line, you can see that originally your line had a positive slope of 1, but now that slope has been reflected to a negative slope. We can also see that the x-intercept of these functions is still 0, 0. And we can see that the y values on the original function of negative 2 and positive 2 have both been flipped from negative 2 to positive 2 on this side, and from positive 2 to negative 2 on this side, whereas all of our x values have remained the same, as we had positive 2 over here and we still have positive 2 over here. and here we had -2 for our x value, and also -2 here for our x value. Essentially what this tells us in terms of points on the original function as it's reflected is that the x-coordinate of the point remains the same all along the reflection. However, our f of x value or our y value has been multiplied by -1, and that factor of -1 tells us why our -2 here is flipped to +2 as we multiply it by -1, and over here why it's flipped from +2 to -2 as we multiply it by -1. Now let's look at the second scenario in which we have a different line which is not the parent function of f of x equals to x. Instead, this function is graphed as f of x equals to 2x plus 1. So in this case, our y-intercept is not 0, but it's 1, as we can see here, 0, 1. And our slope here, or gradient, is +2, which tells us this line is steeper than the parent function. So for every increase in x by a value of 1, you're increasing upwards by a value of 2 along the y-axis. And the 2 points outside of the y-intercept are 1, 3 and -1, -1. So in this case, our y-axis is the line of reflection because we're reflecting across the y-axis, and therefore I've marked it with the crosses. So let's say that you were standing at the point 1, 3 and you were looking at the mirror over here. If you look at the mirror over here, you'd see a reflection of yourself behind the mirror, just like in real life. And if we do that, you get that the point of your reflection would be at around this point. And this point would be -1, 3. So we can see that your x value of +1 in the original function of 2x plus 1 has been flipped by the negative sign towards here. But you also notice that your y-coordinate in this point, the +3, has not been changed. It's still +3 as you reflect it. Similarly for the point -1, -1, if you look at the mirror over here this time, then you'd see a reflection of yourself behind the mirror over here, and that point would lie at this point, and this point would be 1, -1. For this reflected point, just like the reflected point of 1, 3, we can see that our x value has changed from -1 to +1, but your y value is still -1 for both of these. So this tells us that if you plug in f for some x value in the original function like 1, that will equal to the f of the -x as you see over here. So we saw that if you plug in f of 1 in the original function, then that will equal to the f of the reverse of this one, which would be -1, because we know that f of 1 was +3, but that 3 is also equal to f of -1 because -1 gives us 3 on this graph, on the reflected graph. So f of 1 is also -3. We're not changing the entire function's value, we're only changing the value of the x, as we're multiplying the x by a factor of -1. So unlike the previous example, our function this time would be f of x turning into f of -x as we reflect it across the y-axis. And if you connect the dots for the reflected line in the red, you can see that your y-intercept is still the same. However, your x-intercept is not the same anymore. In this case, your x-intercept is at this point for the reflected line, while your x-intercept for the non-reflected line, your original graph, was at this point behind the y-axis. So 2 more things to note from the scenario are that your x-intercept will be changed, however your y-intercept will remain the same as 0, 1. And we know that the reflected function is the reflection of f of x along the y-axis, and that gives you the function f of -x. So if you do a calculation to find the function of this red graph, then you know that f of -x would mean that you're changing the x value in the original function, 2x plus 1, and you're replacing the x by -x as you're plugging in -x in your reflected function. So your f of -x would give you 2 times -x plus 1, and that will equal to -2x plus 1. And you can see from this reflected graph equation that your slope or the gradient is -2, but your y-intercept is still +1, which is the same as your original function that you had over here. So this proves graphically and algebraically that your x-intercept will change, but your y-intercept will remain the same. So let's just do a few examples to see algebraically how reflections along the x-axis and the y-axis affect our original function. So in this case, we're given that f of x equals to x plus 5.2, and we're asked to find f of -x. From the scenarios we just did, we know that f of -x means that you're only changing your x values, but you're not changing your y values at all, because f of -x will equal to f of x for all x values that you pick. And we also learned that f of -x means that we're reflecting the line x plus 5.2 along the y-axis, which also means that our y-intercept will remain the same. So to solve this f of negative x means that you'd have to substitute x for negative x, and that would give us negative x plus 5.2. So your y-intercept is still 5.2 as you saw in the original function and in the reflected function, but your slope has been changed because of that negative x. In this second example, we're given f of x equals to 2x plus 25. In this case, we're asked to find negative f of x. From the scenarios we just did, we know that if you're multiplying negative 1 to the whole f of x, that means that you're only changing the y because you're multiplying negative 1 to the y, but you're not multiplying it with the x that's inside the function. So your x will remain the same, but your y will be reflected by that negative 1 factor. So what this tells us is that we're multiplying the whole function f of x, 2x plus 25, by negative 1. And if we do that, we get negative times 2x plus 25. And if we simplify this, we get that the reflected negative f of x would equal to negative 2x minus 25. In this case, notice that our slope has been changed from 2 to negative 2, but in this case, our y-intercept is also changed from positive 25 to negative 25. But our x-intercept, if we graph these functions, will still be the same. In example 3, we're given that f of x equals to x plus 2, which is the x component of the function, plus 5, which is your k. So we can see that this is a combined function of the linear function transformations. But we also have a combined reflection transformation because we're asked to find the negative f of negative x. So we're not only multiplying negative 1 with f of x, we're also multiplying x by negative 1. So in this case, we're reflecting along the x-axis and the y-axis. So in this case, our negative f of negative x would mean that we're swapping this x for negative x. So in this case, this negative f of negative x means that we're going to get negative times the entire function of negative x plus 2. So we change that x with negative x plus 2 and we get plus 5 here. So this combined reflection transformation would mean that you're multiplying negative 1 by the entire function x plus 2 plus 5, and you're changing the x with negative x. And you can simplify this further on if you want. And this is it for section 3.6 part 2. I hope you found this video helpful, and leave a like if you found this video helpful and subscribe for more videos.